Next speaker is Robert Mello Koch, and he's at Huzhou University, and he's going to give us a talk on why unsupervised deep networks generalize. So please go ahead, Robert, whenever you're ready.
Thanks very much. So thanks for the invitation to this wonderful workshop, and thank you guys for organizing it. I've certainly enjoyed all of the talks I've seen this week. Just a pity that I couldn't be in Italy in person. Okay, the work that I'll be talking about today appears in this archive paper, if you want to take a look at it. It was done with family members, so with my daughter Anita, who is now pursuing a PhD at Brown, and my sister Ellen, who was an academic in Johannesburg, but has now joined the machine learning group at Vitality in London. A lot of the talks that we've heard this week are showing you how useful deep learning is to learn about physics, or as Yang was just telling us, certain aspects of mathematics. I want to do the opposite here. I want to show you that in fact, physics has got something to teach us about how deep learning works. At the moment, deep learning is really this black box, incredibly successful. Nobody can doubt that it works, but why does it work? And in particular, I'd like to make some comments on a puzzle known as the generalization puzzle. So a rough outline, I'm going to start off with really a cartoon of deep learning, very basic and pedagogical, just to motivate exactly what the generalization puzzle is. Once I've motivated what the generalization puzzle is, we'll look at a restricted Boltzman machine, which we'll train on Ising data. And based on those results, we'll be able to see the appearance of RG. And this is actually going to suggest a resolution to the generalization puzzle. And then finally, I'll show you that if you look at computer vision problems more generally, so not just Ising, you'll find that the RG link is quite useful for resolving the puzzle in those cases too. If you have any questions, please stop me during the talk. Okay, so what is machine learning? Well, it's basically curve fitting, right? Imagine, so here's a real cartoon. Imagine you took some measurements of pressure and volume of an ideal gas and temperature. You could take these noisy measurements and you could put a curve through these noisy measurements. And if you've got enough data samples, you'll get a good approximation to the curve. And then you could start to pick pressure and volumes for which you've never measured the temperature, but you can make a prediction. The important thing that I want you to take from this slide is curve fitting. Okay, so that's really the way that a lot of the practitioners of deep learning think about deep learning. It's a form of curve fitting. Now, of course, this is a bit ridiculous. This approximation is too simple. In a real problem, so with something that's called supervised learning, you would be given a list of, I don't know, maybe 20,000 images. Each image would be labeled as cat or dog, 0 for dog, 1 for cat, and you would train your machine. The goal would be that you want the machine to give a 0 or a 1 for an unseen image. Now, in this case, in fact, you might wonder, will the machine even succeed? Well, it does succeed. We all know by now that they do extremely well. But there's probably no elegant law in this case for what it means to be a cat or a dog. So it's a perfectly valid question to ask, what is the machine learning? Now, we're actually going to be focused on unsupervised learning. So in this case, instead of having sets of data that are labeled, the data will actually be an unlabeled list of numbers. And what the machine tries to do, it tries to learn patterns in the data. So it tries to construct a best guess for the probability distribution defined by the data set. So you might wonder, what would unsupervised learning be used for? Well, there's a few very common applications. One is you may have an image that's corrupted. Perhaps, you know, it's got a few spots missing, or there's some water damage. What an unsupervised network could do, it could fill in the missing patches of the image by learning the patterns and the patches of the image that you have. Another place that you've all seen it in action is when you go onto YouTube and you've watched a video. When your video ends, YouTube makes a couple of suggestions for you for what you should watch next. That's an example of unsupervised learning. In that case, you're using something called a deep belief network to do collaborative filtering. That's basically given by stacking restricted Boltzman machines. That's the network that we'll be looking at. Unsupervised learning is also used for things like anomaly detection. So if you want to detect credit card fraud, an unsupervised network could do that. Even by looking at activity on a network, you can actually detect hacking attempts. So unsupervised learning has got many applications. And just a cartoon of what deep learning actually is. So you have this network, it has a number of parameters, weights and biases, and you try to tune these weights and biases so that you produce the desired output from the input. So the training, which would be this label set of data, you would put in the picture of a cat and tune the weight so that the output says cat. How many parameters would a network have? Well, nowadays, easily hundreds of millions of parameters. So imagine you give each of those parameters a dial, you're tuning 100 million dials simultaneously to get the output. When I say simultaneously, let's contrast that to, say, the radio in your car. When you turn up the volume of the station, you don't change which station you're tuned to. In deep learning, by adjusting any of the parameters, you actually change the effect of the other parameters. So you have to tune all of these dials simultaneously. So it's a problem, like imagine you've got a hockey field full of dials, and you need to tune all of these dials simultaneously to train the network. So what is this very powerful algorithm that you're using to train the network? Well, actually, we just usually use something like gradient descent. So the idea is to define a loss function. The loss function could be the desired label minus the output of the net raised to some positive power. So when the net is predicting everything perfectly, the loss function is 0. Otherwise, it's positive. So you simply just have to walk down to the minimum. When you've reached the minimum, your net should be predicting things perfectly. So anyway, that's the idea. Okay, so that was my very brief introduction to deep learning. Let me now tell you about generalization and the generalization puzzle. So we start off with a network. We'll train it on a training data set. The training data set will typically have thousands or maybe tens of thousands of data points. Training is performed in epochs. So we'll train using the entire data set. After we get to the end of the data set, we come back to the beginning and we use the data set a second time. Every time we use the data set is called an epoch, and training would usually take several thousand epochs. You'll typically stop training when your training error is no longer decreasing. An important parameter which will tell you whether you've successfully trained your network or not is the generalization error. And the generalization error is the difference in the error achieved on training data and the error achieved on unseen data. If the generalization error is small, that means you do roughly as well on unseen data as you did on the testing data. Then you say the network generalizes, and it's a useful network. So an important question to ask is, when do we expect networks to generalize? Now, in answering this question, people used the idea that you are curve fitting. So what intuition do you get from curve fitting? I've plotted here error. You can think perhaps this is the size of the loss function. And I've plotted here model complexity. So as you increase more and more parameters, the complexity of the model increases. If you've got very few parameters, you're sitting sort of over here on the curve, and the generalization error, which is written in test error and training error, is not great, but the test error itself is also not great. The training error itself is also not great. What's happening here is you're underfitting the data. So the data is a collection of points, and you simply don't have enough parameters in your model to follow the trends. So maybe you've got a straight line with a slope, or you can do is shoot a line through those points, and you're really not capturing any of the physics behind this data. As you increase the number of parameters, you get to a point where it's optimal. You have enough parameters that you can actually follow the trends in the data. Now you're capturing the physics underlying the data. And in this situation, your generalization error would tend to be a minimum. If you further increase the number of parameters in your model, you now have so many parameters that you could actually produce a curve that goes through every single data point. At this point, you're no longer modeling the physics that you're interested in, but you're modeling all kinds of noise that sits on top of the data. Here we typically overfit the data. And although your training error continues to go down, your test error, so the error on unseen data, starts to go up. So it's very typical to get this orange curve for the test error, this U shape, where initially the error on unseen data goes down, at some point it reaches a minimum, and then it starts to go up again. That's the intuition for curve fitting. Now, where do we sit with deep networks? Have we got complexities in this underfitting region, complexities in the optimal region, or complexities in the overfitting region? Well, for a deep network, you typically have 20 million parameters easily. And you typically train this with about 50,000 samples. So deep networks are actually sitting way over here in the overfitting region. But if you go ahead and you actually check how do deep networks do, well, the training error goes down. You'd expect this U shape, the red curve, for test data. But actually what the deep net does, it gives you this green curve. So the error on unseen data continues to go down. It might go up slightly at very, very large complexities. But on the whole, just including more parameters in your model, your net does better. So the puzzle is, why don't we overfit the data? And that's called the generalization puzzle. It's an open puzzle in deep learning. So let me tell you some of the approaches that have been taken to the generalization puzzle. So Hinton and Van Kamp suggested that networks with a very flat minima in the training loss will generalize well. And here is the basic idea. So if you have a very flat potential like the one I've drawn here, you can move around, and as long as you don't start to climb the walls, you're roughly going to have the same loss. So effectively, as long as you don't move too much, the problem has become independent of this network parameter theta. So for a flat potential, you start to lose dependence on certain coordinates. And Hinton and Van Kamp suggested, well, flat potentials may have so few effective network parameters that if you count how many parameters you've actually got, you've got roughly the same as the number of data samples. So you solve the generalization puzzle. Numerically, this idea was tested and some evidence for it was found. In particular, sharp minima tend to lead to higher generalization errors. This does show you that you favor flatter minima. The other thing that was done to kind of make this more precise is to quantify flatness mathematically. And it was quantified, the stability was quantified by, the flatness was quantified by the stability of the network's output. So add some noise to the network parameters. If the network output doesn't change, then you've got a flat loss function, okay? So add some noise to your network parameter, you'll move it around a bit over here, but you don't change the performance of the output. In that case, there might be very few effective parameters. So now by adding noise to the network parameters, you can count how many effective parameters there are. This was done by Langford and Caruana. In actual fact, you don't manage to resolve the puzzle. In fact, you're nowhere near explaining why the deep network generalizes. This idea was then taken up by Aurora, and he was using a different notion of noise stability, one suggested by Morkos in 2018. Their idea was, look at how stable the network is to rejecting noise that's injected at the input of the network or at any internal node. If the network, it was basically found that if the network generalizes well, it also tends to reject noise that's injected into the network well. So Aurora and company tried to do some detailed calculations using this idea. And let me give you a flavor of what they were doing. So consider a fully connected layer. So each input neuron is connected to each output neuron. So train the network, you'll get a trained weight matrix. Now calculate the singular value decomposition of the trained weight matrix. When you do that, you find that a very large number of the singular values are small, and you can simply set them to 0. This leads to a very large number of parameters that you can just simply eliminate. In fact, it reduces the number of parameters by a factor of about 10, but you're still nowhere near having a big enough reduction to explain why the deep network generalizes. Okay. So now let me explain what we did. So the basic observation of Aurora et al. Is that you get small singular values, so a lot fewer parameters in the deep network than you'd think. Our contribution was, well, let's push this a little bit further and let's look at the singular vectors. Maybe there's a number of entries in the singular vectors that are also zero. And of course, that's a basis dependent statement. So you have to find the right basis in which to express the singular vectors. And once you use the correct basis, you find that they too have very many components which are zero and hardly any non-zero components. The right basis is given to us by physics, as I'll explain soon. The further the reduction in the number of parameters is by a factor of about 40. So now the reduction from the singular values and from the non-zero components of singular vectors means that you get a reduction in your number of parameters of about 400. And this really brings you into the ballpark of being able to resolve the generalization puzzle. And as a bonus, we learn actually what is the network learning. It's doing one step of a normalization group. And I'll try to convince you of that soon. Okay, so here are some details. So our study used unsupervised networks called restricted Boltzman machines. You can also think autoencoder if you're more familiar with that. So I will review what a restricted Boltzman machine is and how it is trained. Our first example studies an RBM trained on Ising data. And I should say in doing this, we were very influenced by Shataro's work. We heard a very nice talk from him yesterday, and also by work by Dimitrios Diataganas, one of the organizers of the workshop. Now, looking at this trained RBM, we're going to see a close and novel connection to RG. So I think it's not the kind of a thing that people perhaps would usually have expected. And we'll see a dramatic reduction in the number of parameters. Now, of course, the Ising dataset is special. So if you wanted to play devil's advocate, you'd say, well, this has got nothing to do with deep learning in general. It's only related to deep learning, the Ising dataset. So what we'll then go on, we'll again use RBMs, but we'll train them on some of the standard image datasets from computer vision. And we'll see the same novel connection to RG, and again, a reduction in the number of parameters. And we'll argue that this provides a clear resolution to the generalization puzzle, at least for this class of networks. Okay, so what is a restricted Boltzman machine? So we have two layers, a visible or input layer and a hidden or output layer. So these circles colored in blue are the input neurons. The circles colored in pink are the output neurons. The parameters of the network, we have weights connecting each input to each output neuron, and each neuron also has a bias. How many neurons are there? Well, we're going to be inputting 80 by 80 lattice states of Ising. So 80 by 80 tells us we've got 6,400 input neurons. And we'll be outputting some state of a 40 by 40 lattice. So we'll be outputting 1,600 neuron values. What parameters do we have? Well, we have 6,400 input biases, 1,600 output biases. And then because we've got a connection between each visible neuron and each hidden neuron, we've got 6,400 times 1,600 weights. And that gives you 10,240,000 weights. So you can see the bulk of the parameters of this network sits inside the weights. The training data set that we'll use has got 40,000 samples. So we've got over 10 million parameters and roughly 40,000 samples. We're very deep into the region where we would expect the network to overfit. For this particular example, training takes about 6,000 epochs, and that takes about 6 hours on a GPU machine. Just to stress this final point, the number of parameters is about 256 times the number of data samples. So we're really in the severe overfitting regime. Okay, so what is a restricted Boltzman machine? It's what's called an energy approach. So we define an energy. What goes into this energy are the biases. The B superscript H and B superscript V are the biases for the hidden invisible neurons. and the weights also go in, as well as the values of the neurons, VI and HA. Once we've got the energy E, we define a probability distribution, which tells us the probability of observing some configuration of V's and H's, and it's basically given by the exponential of minus the energy. This takes the Boltzman form, so that's Boltzman in restricted Boltzmann machine. The fact that it's restricted reflects the fact that I don't allow any connections between visible layers and no connections between hidden layers. How are we going to train this thing? Well, for our loss, we're going to take the relative entropy, as we refer to it in physics. It's also called the Kullback-Leibler divergence. The relative entropy takes in two probability distributions, which I've called Q and P. The relative entropy is always positive or zero. It's zero when the distribution Q is the same as P, and if Q and P are not the same, it's some positive number, which you can think about as the distance between these two probability distributions. So we're going to minimize the relative entropy. When we hit the minimum of the relative entropy, the machine is actually learning the distribution of the data. So Q would be the distribution of the data, and P is the distribution defined by the restricted Boltzmann machine. To minimize this using gradient descent, we need to calculate the derivative of the relative entropy with respect to the weights and the biases. And as you can see on the slide, those are simply given by the differences of certain correlators. To spell out what these correlators are, so we start off and we've got some visible vectors V hat. So V hat would be lattice states of this Ising system. V hats were generated using Metropolis Monte Carlo algorithm, and we generated about 40,000 of these lattice states. For each such lattice state, you can plug them into this equation 1, and you can use this to sample a set of hidden vectors that I've called H hat. Once you've sampled these hidden vectors H hat, we can then plug them into a probability distribution shown in 2 and sample to get V tildes. Once we've got the V tildes, we can use them in the same way that we use the V hats and sample to get some H tildes. So the data was V hat, we used that to sample H hats, we used the H hats to sample V tildes, and we used the V tildes to sample H tildes. We then formed the correlators as shown in equations 3 and 4 using these various variables. Once we've calculated those correlators, well, then we can update all of our network parameters just using standard gradient descent. Okay, so we're using Ising model. I think everybody's familiar with Ising model. It's a nearest neighbor interaction. It tries to align spins. So at very low temperature where energy wins, the plot just looks one color. All of the spins point in one direction. At very high temperatures where entropy wins, you get the speckled plot where there's ups and downs and not much is happening. And then there's some sweet spot in the middle, which is at the critical temperature where energy and entropy are really competing. And you're getting some blocks where spins are aligning, but on the whole, there's also regions where you're not aligned. So that's just the old physics that we're familiar with. Now, I want to remind you of how we do RG for the Ising model. So this is sort of the standard RG. This is what people like Kadanoff were playing with when RG was being discovered. So each of the circles on this page, so 8 by 8, a total of 64 circles, represents a spin sitting on a lattice. What RG will do, it will be a procedure by which we get the long distance, low energy physics, and it does it by performing a kind of coarse graining. And what happens is you group the spins into groups of 4, as I've shown. You average the values of those 4 spins, and that gives you a new block spin. And you start to work out the dynamics for these average block spins. So after one step of RG, the 64 spins that I've shown here would lead to 16 block spins. If you did another step of RG, the 16 block spins would then give you 4 even coarser block spins and so on. And if you had an infinite lattice, you could simply keep repeating this process. And in the end, you'll get some effective theory that's capable of describing the very long distance physics of the problem. Now, I mentioned that we will make a novel connection to RG. So let me explain to you what I was meaning. On this plot over here, the solid circles are again the spins of your lattice. The big asterisks are your block spins. If you look at the asterisk colored in blue, I've got a square drawn around this asterisk colored in blue, and there's a total of 16 spins caught inside that square. I will average those 16 spins to produce the block spin that is blue. Notice that to produce the green block spin, I average all of the spins sitting inside this green square. So some of the spins that I average to get the blue spin, I'm also averaging to get the green spin. And in fact, when I calculate the red spin, there's still more overlap, and some of those spins were already averaged to get the blue spin and the green spin. So this novel form of RG is that we allow the block that we're averaging to become so large that it starts to overlap with neighboring spins. And it turns out that this type of RG is what the RBM is doing. So let me show you how we compared RG and the RBM. So there's the energy function for the RBM, and there's the probability distribution that we use. And in this last equation on the slide, I've shown you what is the probability distribution that we use to sample, for example, the hidden spins. After you've trained the network, you find that the trained bias is very small, typically about 0.01. The trained weights are about 10. So if you calculate what these probabilities are, they're always close to 0 or 1. So the problem basically becomes deterministic. And as long as you're not too worried about normalizations, you can think that HA is essentially becoming the sum over I, the weight matrix multiplied into the input neurons. So we get some sort of a linear relationship between the hidden spin and the visible spin. It's not exact, but this is an approximation. Give you an idea of what's going on, basically because this probability is always a 0 or a 1. If you look at coarse graining, well, to coarse grain something, so for example, if we were doing the 2x2 blocks, we would simply add the 4 spins sitting on the corner of the block, divide by 4, and that would give us the block spin. So the coarse graining is naturally written as some linear operator acting on the input spins. Now, with our approximation for the RBM, the output neuron is some matrix acting on the visible neurons. So the goal to compare a normalization group in RBM is I'm going to be comparing this weight matrix, the trained weight matrix, to the matrix that gives me the coarse graining rule. When I look at the singular values of these two quantities, the RBM singular values are what's given in this dashed line, and the RG is what's given in this orange line. So they show a very similar kind of a behavior, suggesting that they're doing something similar. To get the orange line, we did an RG averaging where we averaged blocks of 16 by 16. So we were averaging 256 spins to get each block spin. So there really was a lot of overlap between the blocks. We worked everything at just above the critical temperature. As you change the temperature, the network changes the size of these blocks that it uses to do the averaging. Once we saw this, we then asked, well, let's take a look at the singular vectors. And does this connection to a normalization group suggest something for the singular vectors? And indeed it does. So the right singular vectors are 6,400 dimensional vectors. Remember, they came from, they are some lattice state of some 80 by 80 lattice. And the left singular vectors are some lattice state of some 40 by 40 lattice. If we really are doing RG, you know, renormalization group keeps the low momentum modes in Fourier space. Those are the long distance features. And it throws away the high momentum modes or the short distance features. So what we decided to do, we took a Fourier transform to momentum space. And then in momentum space, we averaged the magnitude of the entries of the vector that lay inside these radial bands. So for example, this blue band over here would be the sum of the magnitudes of entries in either the visible or hidden singular vectors corresponding to low momentum components. So we've used the lattice Fourier transform. And inside this red circle, it would be the magnitude of components of the visible or hidden singular vectors corresponding to very high momentum. And if you believe that RG is going on, then we would expect the singular vectors to have most of their support at low momentum and very little support at high momentum. So now taking the trained weight matrices and doing a singular value decomposition, this is what we find for the Fourier transforms of these singular vectors. The first one has a singular vector of about 140. The next one has a singular vector about 135, and the next one about 133. So these are all big singular vectors. The input singular vector is plotted as blue. So that would be the magnitude of the radial average of the Fourier transform. And the output singular vector is in orange. So you can see the orange and blue vectors lie on top of each other. The difference is that the orange vector does not have the high momentum components. So these small singular values, the large singular values really are just extracting the low momentum components of the data. What about smaller singular values? Well, here are some singular values all around 7. And what you can see is that the visible and hidden vectors have support for the full range of momenta. You don't see it dropping off at high momentum. And the visible and hidden vectors just simply don't look anything like each other. Now, I want to remind you what is the recipe for a normalization group as we do it in momentum space. So we typically have 3 steps. Split the field into high and low momentum modes. We would then integrate out the highest momentum modes. We would then rescale the fields as well as momentum and position coordinates. And we would repeat this exercise. And slowly, shell by shell, we would eliminate the high momentum modes. If we're very close to the free field fixed point, we could just replace step 2 with the step that says discard the high momentum modes. This is usually always a good approximation, unless you have something like a marginal operator in your theory. And then you know you have to appeal to something like the Kalan-Samanzik equation. You have to calculate beta functions and take into account the flow of those couplings. But that's really because a marginal coupling just simply wouldn't transform under the rescaling of the field. So the integration of the high momentum modes becomes the leading effect in the flow of those couplings. But always for irrelevant and relevant couplings, to get the flow, you can simply discard the high momentum modes. You don't even have to worry about integrating over the high momentum modes. Now, if you look at what our weight matrix is doing, our weight matrix, the singular value decomposition, decomposes it into an input vector, some singular vector, and then the output vector. So if you apply this to any lattice state, this input vector, which looks like the top plot here, those are the large singular values, this input vector extracts the low momentum components of the field, multiplies them by some big singular vector, say 140 or something like that, and then outputs exactly the same spectrum of momentum modes. So basically, for the large singular vectors, you're just taking in the low momentum modes and spitting them out again. If you're looking at the small singular vectors, and this is a lot smaller, about 20 times smaller, these have all momentum modes inside them, but these are essentially getting set to 0 because we set these singular values to 0. And in fact, what you can do is you can define an error, and you can say, I'm going to subtract mode so that the output of the RBM doesn't change by more than a few % or whatever number you decide. And in that case, you can actually work out how many singular values you can discard and how many components of the singular vectors you can discard. Okay, good. So now let's go back to the generalization analysis. How many parameters did we have? About 10.25 million. How many data samples? About 40,000. So a lot more parameters than number of data samples. We're going to keep the first 230 of the 1600 singular values. Let's just go back to the singular value plot. So we're going to keep about 230 of all 1600. So we're cutting it off somewhere here, just past the knee. The other thing that we do is So we managed to get a reduction in the number of parameters by about 1/7. The next thing that we do is look at the radial Fourier transform. We've kept roughly 1/6 of the components that are non-zero. But remember, this is in a radial plot. So if you've got a circle of radius 1/6, you're actually keeping 1/36 of the area. So after you've set many of your momentum modes to 0, you'll end up reducing the number of effective parameters by 1/36. So in total, the number of effective parameters comes out as 1/7 times 1/36 times your 10,240,000, and that gives you 40,635. Now you're in the ballpark of your number of data samples. You don't have a whole lot more parameters than you do data samples. So the number of effective parameters is roughly the number of data samples, giving you some insight into why the network is generalizing. Now this whole thing was automated. We didn't do it by hand. We calculated the mean square error between the output and the output after some parameters are set to 0. And we normalized this by the mean square error of the output. And we said that this must be less than some number eta. The number of parameters drop was fixed by eta. For this case of the RBM, we chose 0.01. But changing eta changes the number of effective parameters that you have. But things don't depend very sensitively on eta. In fact, changing eta a little bit, there's a very sharp point at which you have a very sharp fall off in the number of effective parameters. And then, increasing eta further doesn't really drop any more parameters. I also want you to see where this reduction in the number of parameters is coming from. From the singular values, we got a factor of about 1/7, but most of the heavy lifting is being done by the singular vectors, where we got a dramatic decrease of about 1/36. Now, you might be skeptical and you might think that this has got a lot to do with the Ising model and maybe not much to do with deep learning in general. So we did go on to study some standard machine vision data sets. So we looked at the MNIST data set. This is a grayscale data set of handwritten images of 28 by 28 pixels. We trained an RBM, which has 784 inputs and 196 outputs. So this means you've got a training, set of about 12,000 images, and you have a total of, I didn't say how many parameters, but it would be 784 times 196. You're again very much in the region where you overfit. So there's a picture of some elements of the data set. Here's a picture of the singular values. You can see very large, steep drop off. Here is the Fourier transform of the singular vectors for large singular values. These are some of the large singular values. And again, concentrated at low momentum, and the visible and hidden singular vectors follow very much the same pattern. Okay, so here I've done the generalization analysis. So in this case, we had a total of 153,000 parameters, 12,000 images. Again, we're way too many parameters for the number of data points. We set to 0 a fraction of 75/196 of the singular values. Sorry, these are the ones that were non-zero. And a fraction of 64/324, the Fourier modes were non-zero. And what you can see again, the fraction, the reduction in parameters, most of it is coming from the singular vectors. When we plug in these numbers, we find a number of effective parameters, 11,615, which matches this 12,000 images. Now, the MNIST handwriting data set is considered a very easy data set. A much harder data set is the MNIST fashion data set. So we also looked at this. In this case, they are classified, but we threw the labels away. We're using an RBM. So we're not doing supervised learning. Each image had 28 by 28 pixels. We had a total of 784 inputs, 196 outputs. We trained using 5,000 images, and training completed in about 300 epochs. Oh, one thing that I should mention that I didn't mention, so let me mention it now, is that for each of these cases, you had to initialize your weight matrix sensibly to get a good result. And it turned out the best way to initialize your weight matrix was with a block spin initial And the block spin for 2x2 blocks is what we used. But then after the network trains, it picks its own size blocks and the weight matrix changes quite a bit. Starting with a sort of 2x2 weight matrix initialization speeds up training quite significantly. Okay. There's the MNIST data set.
Hey,
Here
Robert.
again, yep.
So, sorry to interrupt. Just wanted to let you know you have a little less than 5 minutes left.
Okay, great.
Thanks.
So there are large singular values, very few small, very many small singular values. If you look at the Fourier transforms of the singular vectors, again, a very similar sort of a pattern. The input and output singular vectors look very similar. They're concentrated at low momentum. And as far as the generalization analysis goes, our network was trained using 5,000 images. The network had about 150,000 parameters. A fraction of 60 over 196 of the singular values were not zero, and 64 over 324 of the Fourier modes of the singular vectors were not zero. So the total number of effective parameters came out at about 5,226. So again, the number of effective parameters is very comparable to the number of images. Okay, so let me give you some conclusions. So I hope that I have convinced you that these deep learning RBMs are performing a coarse graining, and the coarse graining that they're performing is specifically the momentum space RG near the free field fixed point. So you're just basically discarding high momentum modes. This connection to RG resolves the generalization puzzle because the only parameters that the network really needs are large singular values and the Fourier components, low Fourier components associated to the singular vectors of the large singular values. And if you count this number of parameters in a very wide range of circumstances, the trained weight matrix tries to match the number of effective parameters, the number of data samples that you've got. We've tested this for databases of clouds, databases of flowers, all kinds of different images, and that seems to be a pretty general conclusion. Another facet of the generalization puzzle that I can talk about, but is also puzzling, is that when you start off, you break your data set into two disjoint sets, one for training, one for testing. There's nothing in your procedure and your understanding of curve fitting that would suggest that results should be independent of the way that you're splitting the data set into a training data set and a testing data set. But the independence of the split really is seen for any successful deep networks. So that's again something that appears a bit mysterious, and people have tried to explain it in one way or the other. But it's just a puzzle. Another puzzle that people often talk about is the optimization puzzle. So if you have a function of many millions of parameters, you would expect there are many, many minima. And the chance that by using gradient descent, you're going to get the global minimum is almost zero. So why, in fact, does deep learning work? Why does gradient descent work? And there's been lots of work that has gone into that. I would suggest that these puzzles really come about because you're thinking about deep learning as curve fitting. And maybe if we think about it as coarse graining, we're going to get a better view, and we'll resolve some of these puzzles just by changing the way we're thinking about the problem. So let me give you an example. Think about a system which is just water in some container. If you want to study the physics of the water, you could do it microscopically by knowing the positions and velocities of all of the water molecules. The microscopic description would use things like masses of the water molecules, complicated interaction potentials, things like that. If you're interested in a coarse grain description, well, you don't have many parameters, maybe density of the fluid, viscosity of the fluid, speed of sound in the fluid, a handful of parameters. And the state is specified much more simply by things like just the pressure and temperature of the water. If you've got water at equilibrium, it doesn't matter how you split the water up, just pick any subregion of the water, call that your training data. This will be good enough to figure out the parameters of your coarse-grained description or the trained network. And the fact that the water is at equilibrium tells you that it doesn't matter which piece of the water you choose. So in other words, it doesn't matter how you split the water into a training and testing subsets, you're guaranteed to get the same answer. So I don't know, I feel like there are maybe some possibilities to get some insight into deep learning and how deep learning is working by thinking in this direction. And that's what I wanted to say, so thank you.
Thanks very much, Robert, for the nice talk. So we have some time for questions. Does anyone in either the in-person audience or the online audience? Yeah, I see a question from Sebastian. Would you like to come up front just so they can see you?
Hi, thanks for the nice talk. Can you relate your explanation of generalization to the double descent phenomenon? Like for the people who don't know that there are two different regimes in neural network learning where the generalization error behaves differently?
So I think that's a lovely question. So, to be honest, we've just started thinking about it. So let me just speculate wildly because we don't have any results, but I'll tell you what we're thinking right now. As you increase the complexity, you do find that the generalization error starts to go down, but then there's a point where it starts to increase and you sort of get a little hump, it goes up and then it starts to decrease again. So it seems to me like the early phase of the network is probably doing something like curve fitting. And that's fitting with this U shape that you would have expected for your test error. But as soon as you have enormous networks with enormous complexity, somehow you make a transition to coarse graining. And I think one thing that would be fascinating is to really do more numerical experiments, show that you are making a transition from low complexity, curve fitting, to coarse graining at high complexity, and to actually explore that a bit. So great question. I don't know, but definitely something worth looking at.
Okay, thank you.
Thanks. So do we have any other questions? And maybe while people are thinking, I'll ask one of my own. So I think the comparison between MNIST data and icing was a really nice demonstration that this is a problem-independent phenomenon, but maybe I'll ask then the orthogonal question of, do you expect a similar analysis to be possible for things other than RBMs?
Okay, great. So what's going on here is we have a natural definition of locality, and we use that when we have the Fourier transform. The Ising model comes equipped with locality, and so do pictures. If you've got a photograph and you've got a pixel that's blue, nearby pixels are also likely to be blue. And that's the kind of locality that you're using when you do this analysis. Mm-hmm. So even for RBMs that are being applied, say, to collaborative filtering, you might wonder if this will be successful. So, so that's still RBMs, but different application. So for example, if you've got a bunch of users and they tell you what movies they like, you can write down a bipartite graph where you've got nodes that are maybe white corresponding to the users and nodes that are colored black corresponding to the movies, and white nodes connect to black nodes, but you've got no white nodes connecting and no black nodes connecting. In that situation, that bipartite graph has a natural definition of a Fourier transform. So there is a notion of locality that plays a role in that problem. And you can try to do exactly the same analysis using the Fourier transform on the graph. And that's something that we are looking at now, and it looks promising, but the results are still very preliminary. As soon as you go away from the RBM, I think that the general idea that you've actually got sparsity in your network, so there should be much fewer effective parameters than you would naively think. I think that's correct. But I think the way that you tease that out and understand that, I think probably that's not going to be the story that I told you today. I think making sense of that in more general settings also has the potential to bring some information back to physics so that we understand RG better as well. So I think it's a very nice place where a lot of ideas are interacting and there's still a lot more to be learned.
Great, thank you. So is there any other question from either the in-person audience or the online audience? Seeing none, let's thank Robert once again for a very nice talk.